So today we're going to talk about rational functions, graphs, and discontinuities. So we're going to start by talking about the parent function, 1 over x. So for this case, we have x and y values, and I'll give you an x, and then we'll figure out the y. So if I plug in negative 2 into 1 over x, I get negative 1 half. So at negative 2, it's going to be right here. Oh, that's positive 1. There, that's negative 1 half. At negative 1, well, it would end up being negative 1. And then finally, at negative 1 half, it would end up being negative 2. For those of you that don't remember why that is, if I multiply, if I do 1, and then I divide by 1 half, that's the same as saying 1 times 2 over 1, which is just 2. But in this case, negative, because it was originally a negative 2. So, now you might notice that we have some commonalities there, and that there seems to be a little bit of a curve going on as we look at this equation. Now, let's look at our next value. Our next value says 0. So I'm just going to plug that in. 1 divided by 0. Well, let's see. How many sets of 0 can I divide? Oh no, I actually cannot divide a number by 0. That means that is undefined. Okay, then I'm going to just do my positive ones. 1 half would be 2. 1 would be 1. And 2 would be 1 half. I'll plug in those values as well. Now, what ends up happening as we go on is this should become, well, what if I put in negative 2,000? What you would notice is this would become, negative 1 over 2,000. Which is almost 0. So as it goes further out into the negatives, it gets closer and closer to 0. Same if we go out to the positives. This would be 1 over 2,000. And if I did the opposite, did 1 over 2,000 as my x value, as you can guess, we would end up actually going very significantly higher the closer we got to 0. Meaning our final graph ends up looking like this whenever we graph it. Okay, now let's talk about what happens when instead we're squaring. So if we're squaring, a lot of these things remain the same. Negative 2 would just become 1/4. Notice it's a positive 4. The reason why? Negative 2 squared is positive 4. Meaning at negative 2, it is 1/4. Oh no, at negative 1, it would become a positive 1. At 1 half, it becomes positive 4. I don't even need to tell you that this number gets huge, but it becomes 1 over 4 million instead of 1 over 2,000. And then the bottom parts remain the same. 4, 1, 1/4, and 1 over 4,000. Meaning, you end up getting a mirror image now, where both sides are going up. But we do still have 0, which because 1 over 0 squared is still 1 over 0, is undefined. All right, so let's talk about rational functions, because that's what these are called. Functions with an x in the denominator and or also in the numerator, and always there's at least one in the denominator, are what we call rational functions. The parent function is y equals 1 over x, where x can't equal 0, as we just talked about, because it's undefined, and y can't equal 0, because as we go out we get closer and closer to 0, but as long as we have 1 over that number, it never quite reaches. Most importantly, the graphs of rational functions have at least 2 asymptotes, one horizontal and at least one that's vertical. So what we're going to do is we're going to sketch a graph and its asymptotes. So we're going to start with this one, 6 over x. So if you look right here, this is the equivalent of a when we've been talking about transformations, meaning this will be a vertical stretch. So in this case, that means that at 1, instead of equaling 1, we're going to end up equaling at 1, 2, 3, 4, 5, 6. At 2, it's now going to be 3. At 3, it's 2. And at 6, it's 1. Now these points will be the same on the negatives, just negative versions. Now let's talk about our asymptotes though. So the question is, what value would make x 0? Because I can't divide by 0, and that would be, well, 0. So our vertical asymptote would just be x equals 0, which means our domain, well, let's see. It appears I can have any number in existence except for that, meaning x just cannot equal 0. Now let's talk about our horizontal asymptote. Our horizontal asymptote would also end up actually being y equals 0. Now you might go, but Mr. Peacock, it's now 6 times bigger than it was before. It's no longer saying 1 over x. Yes, but think about it this way. If I have 6 out of a billion, that's not much better than having 1 out of a billion. Your chances are still basically nothing. So as it goes on and x gets bigger, y is going to end up getting closer to 0, meaning our range is going to be y cannot equal 0. All right, let's try another. Okay, so things have changed a little. First thing that we need to do is we need to find our asymptotes this time, because if you look, some things have changed. First off, we have x plus 5. Now, if you remember from transformations, what that means is that our new vertical asymptote is going to move 5 to the left, meaning x equals negative 5 will be our new vertical asymptote. There we go. Now we'll talk about our domain in just a second. Now our horizontal asymptote, well, let's see. That minus 2 is going to change that, so that means it's going down 2, meaning y equals negative 2. That's the same as our k in h and k that we learned from that transformation. So at this point, our graph would be relatively simple. In this case, it would go down 4. But oh wait, we do need to notice it says negative, so 4, 2, 4, and then 4, 2. And it would look something like this. All right. Oh, we forgot about domain and range. So let's go back. Now, in this case, our domain, if you look, is any x value except for negative 5. So we're going to say x cannot equal negative 5. And our range is going to be all of the y values. If you can look, it goes down forever and up forever except for negative 2. So y cannot equal negative 2. All right, so now let's try this one. All right, so this is a squared. So the first thing I need to do is figure out what my vertical asymptote is going to be. So what value of x would make this not work? And in that case, that means that my vertical asymptote is x equals 0, which is also going to be my domain, except for it cannot equal 0. Now let's talk about my horizontal asymptote. So in this case, my horizontal asymptote is going to be dealing with, as I go out to infinity, what's going to happen. And even though I said x squared, it's still going to reach closer and closer to 0 as we go out. So there's that, and let's see. This says -3, which means it's going to be on the bottom. So if I plug in 1, I'm going to get 3 or -3, -3 or -3. 2 will end up being all the way up here. 3 will end up being all the way down here. Leading us very quickly to get close to our asymptotes. So, now let's talk about our range though. Our range in this case is not going to be the same as it was before. Because before, our range was all available numbers because we had some in the bottom and some in the top, except for our horizontal asymptote. But now if you look, the top is empty, as all values in this case are negative. So what we would end up saying is our range was -infinity to 0, but never quite reaches it, so like that. Okay. So now we're going to try this. Now if you look, it's a little bit harder now because we have two asymptotes. By the way, this would be the equivalent of writing x squared minus 6x plus 8. So if you look, we have two vertical asymptotes in this case. They're going to be when x equals 2 and x equals 4. So I'm going to plug those in right now. 2 and 4. That said, as we move out, our horizontal asymptote is just going to be whenever x equals. It's going to be that y is going to eventually get close to 0. Because eventually the -2 and the -4 won't be all that different than just squaring it. So at that point, let's see, our points are going to be at 0. Well, let's find our y-intercept. 2 over -2 times -4, because I'm now putting in 0 for x, so x minus 2 is -2, x minus 4 is -4, so that becomes 2 over 8, or 1/4. Which means I can also say that it's 1/4 right there. Let's see, at 1, that becomes -1 times -3, so 3, so that's 2/3. And there we go. Now you'll notice though we're missing a section, and that's the section right here. So for us to figure out what goes in the middle, I'm going to take the midpoint of this section, which is at +3. So I'm going to plug in 3 to the original equation. 2 over 3 minus 2 is 1, and 3 minus 4 is -1, meaning 2 over -1, or -2. Meaning that is what our middle is going to look like. So let's talk about our domain. Our domain is going to be every value but 2 and 4, so I would say x does not equal 2 or 4. But our range in this case is not all values of y except for 0, because if you look, there is the section from -2 to 0 where we are missing any. So I would start from the bottom, -infinity to -2. Now -2 is included, so we use a bracket. Then I put the u in for unity, or union, and then 0 to infinity. And I appear to have run out of space, but that's what we do for the range. Let's try another one real quick. In this case, 4 over x squared plus 6x plus 9. So if I factored these out, let's see, two numbers that multiply to be 9 add up to 6. That's going to be 3 and 3, meaning x plus 3 squared. Notice that that means that our only horizontal asymptote is going to be at x equals negative 3, meaning our domain will be x does not equal negative 3. Now, as time goes on, we'll see that the vertical asymptote is going to be y equals 0. And so as I plug this in, it's negative, but let's see. 4 ends up becoming, well, let's see. I'm going to get to about here. Oops. Notice that we have no actual extra point in the middle. That's because we only have one, and I mislabeled these, vertical asymptote, and only one horizontal asymptote. Now, let's talk about the range. In this case, the range is only going to be from negative infinity to 0, because there is no middle section to go up. Okay. So now we're going to fill out this little table. Here's our top level. So first we're given an h and a k value. So if we're going to fill this out, it would be g of x equals 1 over x minus h, so x minus 4 minus 2. So let's talk about our vertical asymptote. It's just going to be our h value, so that is going to be x equals 4. And our horizontal asymptote is just going to be our k value, so y equals not negative 4, negative 2. Our domain is just going to be everything but that, so x does not equal 4. Our range is going to just be y does not equal negative 2, and our y-intercept is what is the value when x is 0. So in this case, I would say 1 over negative 4 minus 2, which is negative 2 and a fourth. Okay, let's try another. H is 3. So in this case, we have an h value, meaning, let's see, g of x equals 1 over x minus 3, meaning my vertical asymptote would be x equals 3, and of course my domain at that point is x does not equal 3. But let's talk about our horizontal asymptote. Since there is nothing on the side, that would just become y equals 0, or my range would be y does not equal 0. Now, for me to find the y-intercept, I just plug in 0, and I get negative 1/3. Finally, what happens with this? Well, let's look. I have a k value in this case. The k value is negative 7. But which means, by the way, y equals negative 7, and my range is y does not equal negative 7, because negative 7 is my horizontal asymptote, meaning where it'll never quite touch. But if I do not have an h value, that means that my vertical asymptote is x equals 0, which means my domain is x is everything but 0. So for a y-intercept, when x is 0, that means there is none. It's undefined. All right, so now we're going to write an equation for the translation of the following. We have asymptotes at x over 4 and y equals negative 1. X equals 4, so at that point I would write 1 over, because it's x equals 4, I would go x minus 4, so that my asymptote would be at 4. And then minus 1 on the outside for my value, for my horizontal asymptote. Let's try this one. Oh, this one has two vertical asymptotes. That means 1 over. So our first one would have been x minus 3. And our second would be x plus 4. If we want to multiply that out, it becomes 1 over x squared minus 3x plus 4x is plus x minus 12. All right, now we're going to try one more. If we shift 2 units right and down 6 units, well, let's see. That's 1 over x. Shifting right 2 units is minus 2, because remember, it goes the opposite way you think. And then down 6, minus 6. All right, so now we're going to use the following graphs to write a transformation. So in this case, I'm looking at this graph and I see it's going down 2. That means I would write 1 over x, and because it's down 2, this is going to be a minus 2 on the outside. Now let's look at our next one. In this case, it looks like it's gone right 4. That means 1 over x, but because it's going right, minus 4. Okay, so now we're going to talk about points of discontinuity. Points. All right, a point of discontinuity is basically just the x values that would make the denominator 0. We've been finding these the whole time. It's all the values that were undefined that we were looking for. In the past, they've all been vertical asymptotes, but maybe they won't be as this lesson goes on. Remember, the reason why is because in the math world, horrible, bad, very, very bad, terrible things happen when you divide by 0. Like you get wrong answers. Ooh. So to find a point of discontinuity, we're going to do what you would think would be the horrible option, which is we set the denominator as equal to 0 and solve. Because what we want to do is we want to find out where are those zeros to where are the points that just don't work. So let's find some points of discontinuity. Points. So the way we would find this point of discontinuity is we would take this and we'd factor. So our factors of 12 are 1 and 12, 2 and 6, and 3 and 4. Those are the ones that have a difference of 1, but because it's negative, it's going to be a negative 4 and a positive 3. So x minus 4 times x plus 3. So that means our zeros would be x equals 4 and x equals negative 3. And those are our points of discontinuity. Yay! All right, so now let's talk about this one. So in this case, well, I can't really factor, so I'm going to try this. It equals 0, so I would subtract 4 minus 4. 3x squared equals negative 4. Divide by 3, divide by 3. X squared equals negative 4/3. Square root both sides. Oh, wait. I can't square root a negative without getting imaginary numbers. And if my only points of discontinuity are imaginary, that means that they do not actually exist, meaning that there are none. All right. Now, it's important to know some things about points of discontinuity. They can be one of two different types. We've talked about one type a lot, the vertical asymptote, but this equation right here gives us both. So the first thing I would do here is I would factor it out. So I'm going to factor it now with magic. So if you look at this, like I said, you can see both types of discontinuity on here. I'm going to separate them by doing this. All right. So if you look on the left, we have what we call a removable discontinuity. And that's a whole because it factors out, meaning it's not going to actually, the factors will cancel out, meaning it won't really look different on a graph, but there will be an undefined right at the point that this counts. So in other words, x is going to equal negative 2. That is our point of discontinuity, but that is what we call a removable discontinuity. Now, on the right, you can see that we do not factor out. And because of that, we have what we call a vertical asymptote, which is the ones we've been finding up until now. And if you look, the vertical asymptote is based off of what's once again in the denominator. And so x minus 1 means our vertical asymptote would be x equals 1. Now, I've had some people ask me, but Mr. Peacock, what about that x minus 3? Well, x minus 3 is an important thing as well, because x minus 3 is one of the things we could use to find our, well, roots. So a root is where the function crosses the x-axis. In order to get a root or roots, the numerator is set to 0 after we simplify our function. So let's look at some examples. So we're going to describe any vertical asymptotes we have, removable discontinuities, and or roots for each of our graphs. So first we're going to talk about vertical asymptotes. Well, before we can do that, we need to see if there's anything we can factor. So I look at the top and our factor is x minus 2, and on our bottom, neither of those two factors are the same. So nothing is factorable, which means I can already say that there are no removable discontinuities. But now let's talk about our vertical asymptotes. X plus 1 gives me a vertical asymptote of x equals negative 1. X plus 3, let's use a different color, gives me a vertical asymptote of x equals negative 3. And then x plus 2 is in the numerator, meaning that's going to be one of our roots, and that is going to be x equals 2. So remember, on our left side, that stuff is going in the denominator, and the stuff on the right ends up going in the numerator. All right, let's try this one. So the first thing I have to do is factor out the top. Now, I would normally just use difference of squares, but if you've forgotten it, one thing you can always do is go x squared plus 0x minus 1. Well, what two numbers multiply to be 1 and have a difference of 0? Well, 1 and 1 do, meaning one of them has to be negative, or x minus 1 times x plus 1. If you've forgotten the reason why, that's how it works. So, wait a second, and all of that would be over x plus 1. That way I can go like this. Goodbye. So let's see, are there any ones that cancel? Well, wait a second, x plus 1 cancels, meaning that is a removable discontinuity. So we have one at x equals negative 1 from that. Now, if I look on the bottom, you'll see that there are no others, so I'm going to say none for my vertical asymptotes. And finally, this would be my other top variable, my numerator part, my numerator factor. And so that means that's one of my roots, is x equals 1. We've talked about roots before when we did just normal factoring of polynomials. So, vertical asymptotes. Let's see. First, I need to factor out the bottoms. So that would be two numbers that multiply to be 6, have a difference of 1, x plus 3 times x minus 2, all over x minus 2. So let's see, can we factor anything out? Why, yes, we can. We can factor out x minus 2. That means we have a removable discontinuity at x equals positive 2. Then we have another part, x plus 3. That is in our denominator, which makes it a vertical asymptote since it hasn't been canceled out, meaning x equals negative 3. Finally, we have our roots. Oh, we're missing any, so there are none. Okay, let's try this one. In this case, x squared plus 3x. That becomes x times x plus 3 all over x plus 3. So let's see, is there anything I can cancel out? Why, yes, I can cancel out x plus 3. That means we have a removable discontinuity at x equals negative 3. Then I look, do I have any other vertical asymptotes? Nope. So that's a none. And then finally, if I have an x by itself, that means my root is just x equals 0. You know what? That's the end of our lesson today. Please remember, if you want to look at any of my prior lessons, then please go through and look at my account. And please have a good day. All right.